Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Christian Tapas. Christian is here from the university, or from Caltech. Going to talk to us about speculative execution. He's of course interviewing with the OS group. He has so Christian. I asked Christian what his hobbies are and stuff, and he has a 5-week-old son, and a son that's almost 2 years old. So his children are his outside interest for the time being. Anyway, it's my pleasure.
Thank you very much for your kind introduction. So my talk today will be about distributed speculative execution, which is a programming model that I introduced as part of my PhD research. Before I go into the details of this work, I'd like to give a little motivation behind it. And the first thing that I'd like to mention is that I believe software reliability is important, but not only because a software bug would make some home users unhappy for not being able to watch their favorite movie or for losing their MP3 music collection. As software-driven devices have become ubiquitous, this issue of software reliability is becoming an issue for other domains, like car manufacturing. And think about 5 years ago. If your car engine was stalling, you'd say, "Oh, yet another mechanical problem. I have to take this to the mechanic to fix it." Well, not anymore. These days, we can blame this kind of problems on software. And what comes to mind is the Toyota Prius example from a couple of years ago, when a software glitch in the computer on the Toyota Prius was causing the vehicles to stall at certain highway speeds, and this was causing some safety issues for the car owners. And it's not that we don't care about software reliability, but I believe software reliability is is difficult to achieve. I'm going to show you here briefly just a couple images that show some errors that you don't necessarily want to see. You walk through a mall, you don't want to have all the walls painted with error messages. We can also see another error here. Both the bank and the customers are losing money. But what's really the point that I'm trying to make here is that the other problem that we have to think about is think about reliability and software reliability beyond a single device and the single program. Here, this ATM machine is actually part of a bigger network. So maybe the problem that caused this was not necessarily a fault on the local program, but maybe because something on a remote machine failed, caused this to fail. So we need to focus not only on single devices, but also push this a step further and look at distributed systems. And this is a picture that I took in Rome a couple years ago, actually 3 years ago. And I have to tell you that before I took this picture, I was sure that nothing wrong could happen in critical places like airports and planes, as far as software goes. But when you see this, it makes you think, and it makes you wonder. Maybe we don't know how to write software for the kind of distributed environments that we're seeing these days. So hopefully we won't get to a stage where some really, really critical piece of code that's running one of the a plane or something crashes because we didn't understand the system and the interaction between these components.
We nearly did on the Mars rover.
Yes. So what can we do? And by we here I mean a generic research community, the industry, and so on. As the problem with software reliability is not because necessarily we have bad programmers. It's also the fact that software reliability is expensive. And what we need to do as researchers, I think we need to build new programming models that would make writing reliable software simpler, easier, cheaper, so that everybody can afford to write these kinds of distributed software. We also need to come up with models that would allow programmers to think about, fault tolerance better, and that would allow them to specify scalable or large-scale system in an easier fashion. But also something that not many people really do understand these days, especially in the academia, is that we really need to focus on creating models that would make programmers think about the computation that they want to build, rather than memory allocation and deallocation, or how do you write a recovery code and so on. So we need to separate these two, the computation from the error recovery code, and just make that transparent to the user and the programmer. The other thing I think we should look at is how can we specify these large distributed systems? What does it mean to specify a component? If I have two programs that I know they're correct, what happens if I run them in a shared environment? Would they still perform to the specifications that they have? Would their correctness be affected by this composability? And we need to come up with ways of reasoning about these systems that we can then port to building programming models. Last but not least, I think we also need to come up with tools that will allow us to debug these distributed applications. There might not be necessarily typo bugs, type-like bugs that we have in our code. There could be some conceptually wrong things with the code. So we need to have the tools that can handle the types of system that we're building these days. Well, enough with the preaching. And right now I'm going to describe you briefly some of the projects that I've been working on as a graduate student. And a really great thing about Caltech is that they really don't force their students to take on one particular project and go with that all the way to the end of their PhD. They give graduate students freedom to get involved in other projects, work with people in even other departments. And this is what I actually did for my first year. I was collaborating with people in the control and dynamic systems department. And they had this wonderful wireless test bed for multi-vehicles where they're checking dynamics on them and so on. But the problem that they had there is they had these cooperating robots using a static configuration file for who should take control of the group if one particular robot fails. And there was no good reason for that. They simply just didn't know how to do this right, because they were really concerned with another problem. So I came in and said, well, what if I come up with a dynamic leader election algorithm that would be suited for this kind of wireless environment that you're working on, something that would be fault tolerant to a certain extent, and that will allow you to dynamically configure who takes control based on some metrics that matter to you. So I did this, and they were very happy. It made their system more versatile and more robust. And this project was actually the origin of another challenge that I undertook, to build a fault-tolerant group communication library. As I was writing this leader election protocol, I realized that I need means to communicate between processes, small groups of processes in a reliable manner, and that I needed to have ways to specify the membership of these groups and so on, while preserving certain invariants and reason about the correctness of this protocol. So I went ahead, and now this project actually has a life of itself. We have a new graduate student and another graduate working on this, and they're trying to push this further. I also worked on another project where we're trying to build a trusted compiler. So I joined a group of people from the compilers group, And what we tried to do there, we tried to reduce the amount of trusted code in the compiler to a small set of rewrite rules. These rules were written in a textbook-like manner, the transformations of a program. And then we used a rewrite engine of a theorem prover, which was called MetaPerl, developed kernel, to apply these rules, these transformations, to take the program all the way from source to assembly language.
Trusted, you mean proven correct?
Well, trusted meaning trusted rather than necessarily proven correct, because the proofs that we're doing were by inspection of the rules. So the rules, we looked at them, we made sure that the rules were correct, the transformation that we described were correct. And we knew that the rewrite engine was applying the transformation correctly. So the rewrite engine of the theorem prover was proven to be correct. So that if you specify a certain transformation, that the transformation itself would be applied correctly. So what we had to do, we inspected the rules, make sure that those were correct, and also the glue code that was specifying the order in which you wanted to apply them. So it wasn't really proven, was proven by inspection, if you want, by saying these rules, but it was more of an exercise to see whether we can do certain things with them.
Where is the theorem prover being used?
The theorem prover is used just to apply these transformation rules, these rules. So the transformation rules that describe how a program, how the state of a program transforms from one state to another. If you want, but the main reason we actually used the theorem prover was because we trusted the rewrite engine and we didn't have to do any internal allocation for state and all this. It was all done through simple transformation of the code.
Which programming language did you compile?
We compiled a subset of OCaml, functional language. So. And the way we worked, actually, we had, this was the the core of the system, and then this was the core of the system. We only had recursive functions, and then we added new features to the language, like arrays, integer, some arithmetic, and Boolean operators. And these were just extensions of the correctness. The other thing, the other interesting thing about this compiler was that we had a set of rules here that describe just how functions were transformed. And then whenever somebody wanted to add a feature, they came up with a set of new rules, like 9 new rules for type inference of arrays, another 17 rules for the type checking of arrays, and so on. But these new rules that we were creating did not affect the correctness of the existing rules. So these were independent. So the nice feature of this compiler was its modularity as well. Whereas in a typical compiler, and this was actually the reason we started this. We had this compiler that we're trying to compile ML code and C code and to a common intermediate representation. But the idea was that it got up to a point where we had, I think, about 300,000 lines of code. And there were like 5-6 people working on this. And every time a new person joined the group for adding a new feature, they would, with a probability of 90% break something else in the system because they had to interact with other components. So we said, well, is there a better way of doing this? The problem, though, with this approach was that using this theorem prover and the description of the rules, we couldn't really do any the analysis of the entire program. So we were only looking at local transformations of the program. So we couldn't really implement many of the optimizations and so on. So, but we just wanted to see whether we can do something different. And finally, the core of my research there at Caltech was coming up with this new programming model based on distributed, on speculative executions in the context of distributed computing. So the rest of my talk is organized as follows. First, I'll talk about why do we need a new programming model. Is this necessarily the solution? I believe it is, and I'll give you an example of how I think this programming model that I introduced will make things better. Also, I will continue by giving you the core of my talk on speculative execution, which, as you will see, is an old recipe with a twist. And we'll see what the twist is there. In the last few slides of my talk, I'd like to talk about an ongoing project, something that we just started a few months ago, that addresses this issue of building tools for distributed systems that will help us, fix some of the bugs that we have. And this is preliminary work, but I think it's very interesting, and I thought it was worth mentioning here. And I'll finally conclude my talk. So, why do we need a new programming model? Well, reliability of distributed systems and reliability in general of software is a difficult problem. So maybe we need something that would help us specify certain properties of the programs that we write that will help us build better programs. And there are also historical reasons. And this graph here is not trying to be comprehensive in any way. It's just showing some of the big players from the C-like family. But what it's showing us is that we need to come up with models that are suited for the ubiquitous computing environments that we're working with these days. And we have seen in the past that the environments have driven the programming languages, and certain programming languages like Java, and the models that they provided, the programmers were there because with the development of the web and everything becoming distributed in the sense where you wanted to share pieces of code and you wanted to be able to run that code safely on your system, although somebody else had written it for you. They were providing this programming model for that particular environment. So, what are we doing now, for the new environments that we're working on, where we have, every single device that we have, cell phones, we have even, the DVDs. Everybody has all these devices have a CPU in them. They might be talking to each other. How do we handle these kind of distributed systems? But mainly, I think we need a new programming model because we need higher level abstraction. For the kind of distributed system we're talking about these days, we would like to be able to say something. I want to achieve distributed consensus between these nodes in the system without really worrying about how this is done. Other people have done it for us, and while it's true, there's not a perfect solution for all the requirements, but for most of the people that want this functionality, what we have there, could be good enough. And also, programmers don't have to reinvent the wheel every time they write this kind of code. Also, maybe we want some distributed optimistic execution, something where a program optimistically executes and involves other processes in its own optimistic execution. But what's really more important, we really need to make writing code easier. And if we manage to make writing code easier, and if we manage to make our codes simpler, then the programs that we write will be shorter, and we'll be able to reason easier about them. I'm going to introduce the concept, the programming model that I worked on through a very simple example. This is, in fact, the classical database example of atomic money transfer. You have two accounts, you want to transfer an amount of money between these two accounts. But I present it here in a slightly different context, where what we really want is we want to transfer two blocks of data between two files. And we want to do this in an atomic manner. So if any of the operations that we have failed, then we want to leave the system in a consistent state. So traditionally, the way you do this, you create two temporary buffers, you read those blocks of data, and you write them into the opposite file. Well, everything is fine if the first three operations either succeed or fail, because then the read operations don't really change the state of the system, whereas the write, if we assume it to be atomic, then if it fails, we know it hasn't really changed the state of the system. But what happens if this write operation succeeds and now the last operation fails? What you have to do in order to leave the system in a consistent state, you'd have to undo the operations of the first write, which might or might not be possible to do. But even if it is possible to do, we have to write all this recovery code in line with our computation just to make sure, that things are left in a consistent state.
This is just for one. You're not having parallelism in here, right?
No, not yet.
All right.
So what if we were to introduce a new programming model that would separate this fault recovery code, this error recovery code, from the actual computation? Something that would tell us, that would provide for us fault recovery for certain types of errors, right, transparently. Something that would make our code simpler. What if we were just to say, well, I'm going to speculate that all these operations will be successful, the read and write operations. Now, if any of them fails, I want the system to do all the work for me, restore the state to what it was just before I entered this speculation, and maybe take a different branch of execution. Just say, I tried this, I want to return failure.
How is that different from a transaction?
Okay, we'll get there in just a second. Okay. So, remember what I said initially. It's an old recipe, but it has a twist to it. So, this is the plain, boring definition that I usually give for transaction. Transaction defines a speculation which is based on an assumption whose verification may be delayed. What do I really mean by this? A speculation, the way I define it, has three components. It has the assumption, which is A here, on which we base our computation. Then it has the what we call the commit branch, which is the branch of execution that gets executed assuming the assumption is correct. And then we have the abort branch, which is executed if the assumption is invalidated. Now, the idea is that speculation is equivalent to either the commit or the abort branch, but not a combination of the two. Right? So if we were to have an oracle that could tell us beforehand what the outcome of the speculation is, then the idea of speculation could be written as the following conditional statement. If the oracle tells us the assumption is true, then execute the commit branch, otherwise execute the abort branch. But in practice, we don't have this oracle. We don't know beforehand whether the assumption is going to be true or false. So what we do is we start executing the commit branch. If everything goes well and at some point we are able to validate our assumption, we commit the speculation. However, if things go wrong, what we have to do, we have to abort the speculation, roll back the state, undo the effects of the commit branch, and start executing on the abort branch. So as far as we're concerned, the commit branch is sort of an atomic operation, and if the assumption is invalidated, then we have to abort those the effects of those operations. We introduce speculation through three programming language constructs. Speculate, that returns an identifier of a speculation. And then we have commit and abort that are called whenever the assumption on which we base our computation is either validated or invalidated. They take the idea of a speculation, and commit doesn't do anything. It just returns void. Whereas abort doesn't really have a return type, because what it does for you is just rolls back the computation and starts executing the abort branch. So it's like it never happened. Well, as you pointed out, speculation shares some traits with database transactions. But when we're talking about distributed systems, and not only in the concept of distributed systems, there is one major difference. You can imagine a speculation being a transaction with no isolation. And while the typical transactions have the ACID property, the atomicity, consistency, isolation, and durability, we chose to relax the isolation property. Why is this important? Well, I believe that for the current environments that we write software for, relaxing the isolation allows for increased parallelism. We don't have to close the world to the program. So all the actions that are performed inside the speculation are visible to the outside world. Well, of course, the impact of implementing such a programming model that has this loose isolation property, it makes implementation really hard, maybe. But that's not the point. This is the kind of models that we want to have, right? Because it increases parallelism. It allows for all sort of interesting concepts like distributed optimistic execution. And we'll see on the next few slides how we can use speculations.
So can you, I guess one of the questions I have is, okay, so you don't execute in isolation,
Yes.
but you do have atomicity.
Well, atomicity in a way.
Yeah, so what do A and C mean in this case? You don't have isolation.
Well, you can still define a block as being atomic, right? As we've seen on the previous example, you say my commit branch is an atomic operation. If something goes wrong while I execute the commit branch, maybe my assumption is the commit branch is atomic. So you see, when we actually program using speculations, you don't have to specify statically what the assumption is. The assumption could be this block is executed atomically, and if anything goes wrong, something prevents me from continuing my execution, then I roll back and maybe take a different execution path. And consistency, what this means is that, especially in the context of distributed systems, it means that if I'm a process and I send information to a remote node as part of my speculation, if I abort my speculation, they will have to do this to roll back their state as well to what it was. We cannot have a computation of another process in the system be based on an assumption that has been invalidated.
You still have the notion of the serialization order?
I'm sorry?
A serialization order?
Yes, what about serialization?
So
sorry.
if one transaction commits before a second transaction, the first transaction has actually observed changes made by the second transaction, and the second transaction aborts.
Right. But we don't have transactions here. So,
Speculations, right?
well, it's different in the following sense that the way these propagate, they're subject to different constraints than your traditional database transactions. So your database transactions typically use or act on some shared database content, whereas here you have programs. You have individual states of the programs, and if a program starts a speculation, commits the speculation, starts another speculation, commits that speculation, as far as he's concerned, this happens sequentially because this is the order of the execution on its local execution thread. And we do have certain dependencies between the series speculations. But the idea of sequential consistency, I don't think it applies directly to programming. You can talk, I think, about the sequential consistency of the data, of a shared data or something, but not necessarily in the. I'm not sure if I understood your question exactly.
So maybe I should put it another way. Do you still have locks in your system?
You could. So speculations is not a solution that would just take care of everything that's wrong with our current computation. As we'll see through some examples in a short while, it can be used to alleviate some of the problems with the existing systems. It could be used to make writing certain kinds of systems easier. But it doesn't try to wipe out the idea of locks. It's not like software transactional memory in that respect, if you want. It's we're trying to provide programmers with some high-level primitives that, for example, they could optimistically acquire a lock and speculate that they will actually receive the lock without having to wait for that lock to be actually passed to them. So they speculatively execute. You gain some useful computation. And we'll see actually through some examples, and maybe that will answer your question. Yes?
I understand the argument that I don't think transactions are well defined in a distributed environment. There's no such thing yet as distributed transactions. But this sounds to be the problem that people address in checkpointing distributed systems. What's the consistent state?
Right. So we actually borrow some ideas from the work done in checkpointing and rollback, because in order to maintain a consistent distributed state for rollback, when you propagate speculative information, yes, you actually have to come up with this safe recovery line, and this is why I actually have here, this black things here are actually checkpoints, as I label them here. And what you really need to be able to do is you need to come up with a lightweight mechanism for taking these checkpoints. So in this respect, I think we're different than traditional checkpoint and rollback. We want to make this usable on a different scale, where when you speculate, we want to use speculations more often in our programs, and when you speculate, you don't necessarily have to halt your program and hold maybe other programs in your distributed system and say, oh, everybody, let's just checkpoint at this moment in time. What you want to be able to do is, I want to remember that when I abort my speculation, I have to roll back to this point. Have a lightweight or an efficient implementation of this rollback mechanism, and combine this with communication-induced checkpoints. So when I send a speculative message to other nodes, upon their receiving the speculative information, they'll have to remember where they have to roll back if I abort my speculation. So we only assume message passing for this particular model that I'll describe today, and communication generates what we call implicit speculation. If you receive a speculative message, you'll become part of this implicit speculation. So on the next 3 slides, I'll provide 3 examples of programs that could be implemented using speculations. The first one is a distributed reservation system. I don't expect you to necessarily look at all the details of this pseudocode for each of the entities. I'm just going to give you the big picture, and we'll investigate certain execution paths through 2 scenarios. But what we have 3 entities: a client, a flight agent, and a hotel. And this is your typical reservation system. The client wants to atomically guarantee that it can secure both a room at a hotel and a flight given certain time constraints and financial constraints. Has only certain budget for this travel. So the interaction that we have between the entities is the following. The client speculates that it will be able to get secure both the hotel room and the flight. So it sends a request for quote both the hotel and the flight agent. On the hotel side, things are relatively simple. The hotel checks the local availability. It looks in their books and they say, yes, we do have a room for your particular date, and here's the price that we can give you the room for. And as you observe here, upon receiving this speculative request, the hotel is acting right now as part of this speculation that the client initiated. Well, with the flight agent, things are a little bit more complicated. What it does is check local reservation, but the flight agent doesn't have the ultimate answer to this question. The airline is the one that has the exact number of people that are registered, because there are several flight agents that can reserve flights on a certain flight. So it speculates that his local reservation actually is consistent with the main information held by the airline, and it sends a quote to the client. This is a nested speculation that flight agent has, and its speculative information will absorb the client in that speculation. The client decides, oh yes, the prices are okay. In the meanwhile, the flight agent receives confirmation from the airline. Yes, indeed, we do have spaces. Let's commit our speculation. And the flight agent commits the speculation. This also notifies the client and takes the client out of this nested speculation. Finally, the client acts in its own way, as described by the program here, sends a payment to both entities, and it secures its travel. Finally, commits the speculation. Well, this is the good scenario. Now, what happens, for example, if the airline says, the flight is overbooked. The other people, there was somebody else who took all the seats from this flight. Well, the flight agent has to abort its speculation. But this triggers an abort both on the flight agent side, but also on the client side. So the client and the flight agent will roll back. The flight agent, at this point, will start executing its abort branch of the speculation and will say, I just received notification, the flight is full. The client doesn't even know that it initially received that statement from that message from the flight agent, because its state is rolled back to what it was just before receiving that message. Now it says, oh, the flight is full. I have to abort. I'm not able to secure this. So what I'll do, I'll roll back my computation to my initial state and try different agents. Okay. So another example that I have here touches on the optimistic speculative execution, especially in the case of a distributed system. Again, there's a lot of information here, but I'll go through it one step at a time. We're trying to implement an optimistic total order protocol using speculation under certain assumptions. And the assumptions are here at the bottom of the slide. It says, we assume that there are reliable FIFO channels between all the entities in the system. And that we also have a bounded network latency. So if I send a message, I know it will get to the other node in a certain period of time, which is bounded. The other, but we don't really know, how long it will take in that particular window to get a message. And actually, messages that are sent given a universal global clock could arrive in different order at their destination from different sources. Also, messages are labeled with sequence numbers, so messages that are sent in the system that are strictly increasing, but they're not consecutive, and they're also unique. Right? So you send a message, you label it somehow, then 5 seconds later you send another message. Even if nobody else in the system sent a message during that time, your identifier doesn't necessarily have to be consecutive to your previous message. Right? So this is an important assumption. Classically, the way you'd implement the total order protocol given this assumption is, well, you receive a message, and because you have bounded network latency, you can guarantee that in a certain time, especially if you have some ping messages that are going on regularly, a certain time you will either receive confirmation that this is the right message to send to your application. So you can imagine it as the protocol that I described here as a layer that stands between the network and the actual application. So you receive a message, you don't know if you can deliver this message to the application right away. When you receive this message, it could be the case that you have to wait until a certain period of time until you receive confirmation that this is the actual message that you have to deliver to the application. So in the classical model, what you do is you receive a message, you wait for a certain period of time, and then deliver a message to the application. The application starts to do some useful computation. The optimistic execution would say, I receive a message, I know most of the time I'm correct, by just saying, this is the next message that I have to deliver to my application. And this is what we do here. You start a speculation, and you say, this is the message that the application should process. If in this safe period, in this period of time, you don't receive any other message that invalidates your assumption, then what the application does, it does useful computation, and then when you receive confirmation that this was indeed the message that was supposed to be delivered, you commit the speculation and you let the application do some more useful computation. So in this case, you actually gain some useful computation by executing optimistically. Well, what happens in the not so nice scenario when another message gets, when you receive another message with a lower message ID? Well, this is described in this graph here. You speculate, the application does some computation here. That's not useful computation. You receive another message that invalidates your assumption. You have to abort the speculation, but what you can do now, you can feed that new message to the application and say, oh, I think this is the right thing to do. This is the next message that you have to process. And you might do this a few times, but eventually, you will receive the next message to be delivered to the application, right? And you don't at that point, you don't have to wait for another period of time to deliver the message, you can optimistically execute, pass that on to the application, and you'll eventually gain some useful computation.
This seems like a very odd set of assumptions. In particular, the sequence number assumption. I mean, this problem is very analogous to the problem that TCP is trying to solve by putting byte sequence numbers in the messages. Why is it an interesting problem that you have a pair of communicating things that can't use consecutive sequence numbers? And where would that happen?
Well, for example, you could imagine having these entities, these nodes, communicating with several groups, and then they increase their sequence number every time they send a message in each of the groups.
Do that, sure, but then you've introduced a hard problem that. So, maybe I misunderstand your problem. You're trying to get sequential ordering on just one pair. Of nodes.
You could have a group of nodes.
You have a group of nodes.
Yes, so it's not between a pair of nodes. You have several nodes in your system, and you want to achieve total order between all the messages that are sent in this.
Total order on all the messages that are being sent.
Yes.
And the total order is this ID number that.
Yes.
That
And
somehow the nodes are responsible for coming up with unconflicting.
Yes, and they can come up with this, but the problem is that this is not actually giving you consecutive numbers.
Okay, so it's like timestamp node
Yes.
ID pair things,
Exactly.
and you want them to happen in that. Okay.
Right.
This makes more sense.
Okay. But this is the behavior of one particular node in the system, and this is why you actually, when I said reliable FIFO channels, when you have just one channel between the,
It doesn't matter.
it doesn't matter. You won't get reordering between those messages, right? Because it's first in, first out. But the problem is when you have a node having two incoming channels.
Otherwise, you'd have to wait for the whole time.
Exactly.
Okay, now
So
I get it.
this is the actual context in which I described the problem.
So can you still have cycles and deadlock in the system? Is there some way to prevent that?
For distributed speculations, you mean, or?
Well, when you have a group of agents, nodes operating, can you get to a situation where two of them are waiting on each other?
When they're, but not sure. Well, in the context of this total order protocol, or in?
Yeah, but basically, can you get it there?
No, because in this, I mean, because you use speculations, no. In general, if the program is not written correctly, I guess you could, but I'm not sure how this question really addresses or is related to this particular example.
So there's no slide coming up. Okay, we can do that.
Sure. This is the last example that I'll use to illustrate, speculations and what can we do with them. This is a scientific computing example where traditionally in scientific computing you have a computation that usually a huge matrix maybe. Then you split this among several compute nodes, node 0, 1, 2, 3, and these nodes have to run in lockstep, and they have to share some border information for each step of their computation. Well, what do you do though if you want to have a reliable program, right? When one of your computation node fails, you want to be able to not necessarily start all the way from the beginning, but use a mechanism that helps you roll back to a more recent state. So traditionally, the way you do this, you checkpoint your application at certain time steps in their computation. It's like a synchronized checkpoint. Everybody checkpoints on step X. But if you're using pure checkpointing for this, then whenever a process fails, not only you have to move that process on a reserve node that you have, to restart that computation, but everybody else has to load their checkpoints from disk, right? And this puts a lot of pressure on the actual storage system that you have at your disposal, right? All the nodes in the computation have to read this, heavyweight checkpoint and restart their state. What if we were to use speculations for this? And what we say is, between every time you hit one of these synchronization points, you say, I'm going to speculate that everybody will make it to the next synchronization point. Then you do this lightweight checkpointing, and I'm going to give you a hint here on how you do it. We do it in memory. So you keep track in memory of this checkpoint. And whenever a computation fails, you only need to restart that particular node from disk, and the rest of the computation is simply rolled back in memory. So you take some pressure off of the actual storage system. And by the way, these examples that, some of the examples, actually, the last two examples that I talked about, we did implement them, and you'll see a movie of how this works actually in a speculative environment shortly.
Kristen, is it the reason that you can do lightweight checkpointing is because your system is programmable, the programmer can use the speculative
Yes.
to selectively have the data.
Exactly, and you can do it in a way that makes sense to the application. You don't have to just blindly checkpoint the entire state of the system. You can even have incremental checkpoints. So, but they're in memory, so there is a certain cost. Nothing comes for free. In the next 2 slides of my talk, I'll actually move on to a more theoretical aspect of my work and try to define a formal model for speculations. And why do we need a formal model? As I mentioned initially, I think one of the problems with writing distributed systems in general is that people just jump into the implementation. They don't really think about, what does it mean to write a distributed program? How does this component affect other components in the system? So as part of my work, I usually like to focus on the formal side of things, understand really the problem from a theoretical perspective. And once I have that, I can move on to the actual implementation. And there are certain benefits for it. One of it is that if you have a really clear formal model, clear specification, then you can make sure, or this increases the confidence in your implementation, right? If you're able to write an implementation that closely matches the specification that you have, then, and if you're able to prove the correctness of your model, then you're more confident in your actual implementation. But there's another reason. Usually when you introduce a new programming model and you want people to use it, if they want to use it with their favorite model checker tool or their favorite debugger, you would actually have to twist the debugger or the model checker to understand these new concepts that you introduce. However, if you have a formal model for this new programming, formal model for this programming model, and then you can show that it's actually equivalent to something that you can already reason about, then what you have to do is, as part of making the tools available, just have some hooks that transform your program into this other model that you can reason about. And in this case, actually, as part of my research, I showed that speculative execution is really nothing more than non-deterministic, non-speculative execution, where when you reach a speculate point, you either take the commit branch or the abort branch, depending on the outcome of the speculation. So if you're able to have simple transformations like this that take your speculative program and show their equivalence with something you can reason about, you can make use of existing tools. You can use your favorite model checker or other tool there to reason about the correctness of your program. So we do have the 3 syntactical constructs that I described before, where speculation has the commit branch, the abort branch. You have commit and abort. And we also have 2 operations that will help us with message passing. A process can send a message to another process PI, and a process receives a message and uses it in its computation described by E in this case. So this is a functional style representation of these things. So what we need to do is we need to be able to capture the state of the distributed system, and we do this by capturing the state of all the processes in the system somehow. And there are 3 main components to this. There is the program that the process executes, which is a sequence of instructions. You have a base language, and I assume there is a similar operational semantics for whatever language you have, and you just extend it with these constructs. Then you have a set of lightweight checkpoints that are created for each of the speculations. We also have a receive queue. We only have one receive queue for all incoming messages. It doesn't matter who sends those to you. And this is just to simplify the model here. There is also an internal state of the process, like local variables and things like that. But this, I didn't put this on the slide here because it's not as relevant, and you just need to know that it is there. So a transformation rule that I have in my operational semantics shows the transformation of the state of the entire distributed system given at most one process in the system executes one instruction, right? So in this case, I know that in this transformation, it was only PI that executed, instruction E1 in its program. And I analyze how this affects the rest of the system. I'm not going to give you all the details of the rules. I have probably about 25-something rules, but I only talk about some of the main players here. What happens when a process PI speculates? Let's assume the process is also already part of two speculations. So what we need to do is we save a new checkpoint that would tell us, well, if you ever abort the speculation, you have to roll back to this particular state. And what we save in this state is the local state of a process, local variables, and so on. But we also save the abort branch. What happens? What should the program execute upon rollback? And as you can see, it doesn't have to execute the speculate block again. It only executes the abort branch and the rest of the program. Right? So this is what we actually save in this lightweight checkpoint. What happens when a process receives a speculative message? This is message M. It's tagged with speculation identifier S. What it happens is the way the state of the system changes is the following. It's very similar to the speculate call because in this case we have an implicit speculation. The main difference here, we still save a checkpoint with the state of the process and so on. The main difference here is that the abort and the commit branch are the same because the speculation is implicit. The program itself didn't specify an alternate execution path upon rollback. It was implicitly absorbed in the speculation, so it only has to, it saves the same state here in this checkpoint, the same program to execute upon rollback. What happens when you abort a speculation? Well, if you abort a speculation that you own, and assuming that this checkpoint here was saved as part of an implicit speculation, okay, this is just one of the abort rules. I actually have, I think, about 8 or 10 of them handling different situations. But what does happen is you have to restore the state you had saved in that checkpoint. So what you do is you take the abort branch, you start executing that as part of PI. But this is actually a twofold process. When you abort a speculation that you initiated, first you have to roll back your state, but you also have to let the other processes in the system know that this speculation has been aborted. So at this point, you don't force them to roll back. You just tell them, this speculation has been aborted, invalidate this checkpoint. And I have separate rules that say, okay, if you have an invalidated checkpoint in your system, you don't really go on with your execution. You roll back to that checkpoint and you extract whatever state you saved and execute that again. So you roll back. Also, if you abort a speculation and you own some nested speculations there, you have to abort those first and then eventually abort the speculation. So there's several rules there, right?
Can you explain a little bit more what happens after you've received a message and now you're in a speculation that gets aborted? Do you roll back to a point where you have received the message, or do you roll back to a point before
receiving the message?
Okay.
Yes. So you roll back to the point before receiving the message. So the message is not in the queue because the message gets invalidated as well as part of the abort process. This is what happens when you abort the state.
So do you immediately try to receive again?
Yes.
Yeah. Okay.
Right. And I understand that there are issues with this model because you're putting some of the work in the hands of the programmer, right? But what happens, right? If your program sends a message and then on the abort branch doesn't send that message again, we can argue that that's actually a problem with their program. And this is the expected thing to do in this case, because you are in a state where you're waiting for a message, and you got some speculative information, you process that, but that was not supposed to be there in the first place. So you roll back to that waiting state, and wait, hopefully, for the initiator of the speculation to send you a non-speculative message or the correct thing. Okay. So just to summarize what we've seen so far on speculations, we define a computation based on a certain assumption, whose verification we can delay to a certain point in the future. And if you really think about speculations in the distributed context, what they are, they extend the exception mechanism, right, to distributed environments. You have an exception triggered on one node, and that forces other nodes that participate in this computation to roll back their state, right? It's very similar to the notion of exceptions on sequential programs. And we're able to define safe recovery lines in distributed environments and provide reliability for certain types of applications, also provide other features like optimistic distributed execution. Okay. And we actually did implement this.
So what happens what if I speculate and I send messages to a bunch of guys and then I go into a long loop, or I become disconnected, or due to a programmer error I don't send a commit or abort for a while? Aren't they all left hanging? Aren't I in live lock?
Well, they do continue with their computation as they would normally do, right?
But they're not allowed to commit anything.
They can commit their own initial.
But they can't send a message to the outside world. They can't send a message out.
They can to other nodes in the system. Well, okay. So there are some limitations to this implementation. If you were, for example, to launch a missile, as part of your speculation, you obviously cannot take that back, right? So, as I said initially, this is not a solution that fits all the programming needs that are out there. There's certain
you can't even print a message or send something to anything outside of your system, and presumably you want to eventually print something saying.
Sure, but it actually depends. For example, for debugging purposes, actually having, as part of a speculative computation, having printouts does help. We actually found out as we were playing with this computer model that, in certain cases it might be actually useful to have some state that you cannot, take back, just for debugging purposes and other things. But it is true when you do some an action that's not non-rolling back, you cannot take it back, then yes, you have to wait until that happens. And usually we put this burden on the programmer to make sure that when they do this, when they write speculative programs, they don't do it in weird ways. However, you can imagine that there are certain operations that you can actually do. For example, what if you were, as part of your speculative program, ask what the domain names are, what's the IP address of this domain, So idempotent operations can still be performed, things that don't affect the state of other processes in the system, in the outside world, right? Things like reading and so on, they can still be. So it doesn't matter if you, as part of your speculation, you query, what's the IP address of Microsoft.com, right? If you take back that speculation, roll back, the name server hasn't been affected.
For automatically aborting ongoing transactions by nodes that die or become unavailable.
By nodes that die. We do. So the way we implement this, if you are in a closed speculative environment and everybody knows about speculations and it just happens that one of the nodes is disconnected, the way I implemented this, and I don't know if it's the perfect way of doing things, if you're not able to communicate with the initiator of a speculation for a certain period of time, you assume the speculation has failed. and you roll back your computation.
Okay, so there's a timeout.
There's a timeout.
And that takes care of the deadlock.
Yes.
So,
But there is, yes.
do you have a reliable synchronous network model, or what's the underlying network model here?
The way, well, I do assume certain fault detection mechanism in the network where I can tell.
Tell the difference between a network partition and a failed node.
Well, you can never really tell this.
Well, if you assume in your model, you can,
But
then you have
yes.
a fairly unrealistic model.
Yes, so the prototype that I have implemented by myself uses a reliable UDP brewed protocol, homebrewed protocol that to detect these kinds of errors. And I just assume that whenever a timeout occurs, it's actually the node that has failed. So I don't really treat network partitions. No, in this system.
So can you just explain why it's important to distinguish between network partitions and node failures in your model?
Because both nodes are running, and you have a distributed consensus is impossible with asynchronous, unreliable networks, and this has it all in one place.
I think there's another point that I didn't make in my slides here, is that the way things work is, as far as the initiator of a speculation is really concerned, it doesn't matter if some implicit speculative node aborts or not. That doesn't affect necessarily. It depends on the assumption that you make. But typically, if an implicit node fails, does not mean that the entire speculation has to be aborted. At least this is with most models that I treated. However, if the initiator of the speculation dies, then yes, everybody has to abort that speculation. Right? So
I've been waiting for you to mention nested speculations. What happens if one process can have simultaneous speculations going?
yes, we can have those.
The problem I'm trying to figure out is, I think for speculate it's fine, you get a unique ID.
Right.
But for abort, especially another process can abort speculation initiated by me, for example.
No, it cannot. It's only the owner, as I was trying to make the point right now, it's only the owner of the speculation that can abort the outcome of that particular speculation.
Case that if the initiator dies.
Yes, if the initiator dies, that means we implicitly say the speculation has been aborted.
So it's a special case in general.
It's a special case. You could go the other way and say the speculation has been committed, but you have to decide one way or another. We chose the more conservative approach.
So what if the initiator commits, says, okay, it does speculation, and then it says, okay, and then it commits something, but after that commit, then it ceases all communication, and before it notifies the other nodes of its commit, it dies. So now everybody else is going to abort, even though something was committed based on the assumption that would eventually commit.
Sure, but okay, you can imagine this from the 2 points of view, right? So from the point of view of the initiator of the speculation, the rest of the world could be dead. So the initiator will still commit its own speculation, right? And now you look at the rest of the world; they never seen that commit message because that initiator has failed. And we also assume, fail stop. You fail, you stop execution. You don't come up with the same ID necessarily and try to. I didn't consider the case of malicious computations and malicious nodes in this case.
I mean, for reliable message delivery, you require that a node be always on. So if I send a message.
Sure.
The only reason why that's reliable is that I'm always going to be available to respond to NACs.
Yes.
But if I send a message and then die,
yes,
then I can't. If I ever am going to die in the future, I can't send reliable messages.
Right, that's true. And I believe that this should not necessarily affect the model that you have. It depends on what you define as consistency. For these in this context, but for most applications that we have dealt with, this was not an issue. So we look at from the perspective of each node, and if the node cannot contact you, it just assumes you're dead. So it rolls back the computation, which is the conservative way of approaching this.
Well, but in your airline purchasing example, that means that the airline sold you the ticket and you go off and buy another one somewhere else. So I'm sure the conservative is necessarily the way to describe it.
Well, you can assume that in certain special cases, you have the programmer. So you see, there's a slight difference here between the propagation of these messages and the other communication that the nodes are doing. So if the nodes are using, let's say, TCP communication, right? You can piggyback some of the speculative control messages on top of that, and provide the same guarantees as TCP does.
And it's distributed systems problem here. Yeah. I mean, you can't get out of this, right? Because it's an impossibility.
Sure, but no. What I'm saying is that for certain.
Yeah, well, two-phase commit works by blocking you forever.
Yes.
Right. So
Yeah.
yes, you can have a protocol that never completes, or you can have a protocol that's incorrect.
Yeah,
But those are the only
those are the
choices.
only
And
two
so the fact that
choices.
he can't solve an impossible problem is actually his fault.
Well, yes, and
As long as he realizes it.
Oh yeah, that's where we're trying to get to.
okay. So just to give you an idea here, so we did implement this as two options. Two different implementations. First, we tried to put speculative execution in part of a custom compiler, and everybody hated it because they had to compile their programs using our compiler. It was slow. It was a prototype compiler. So I decided to move more, if you want, mainstream, and provide this functionality as part of a kernel. I provide support for local and distributed speculation. It's slightly more efficient than the compiler because I did this as part of the Linux kernel because it was available. The source was available, so I could play with it. And the nice thing about the kernel is that it also supports automatic implementations of programs that don't necessarily have an idea about speculation. So you can just trigger or force a speculation on a program the way we do with implicit speculations. Whereas with your compiler, you couldn't do that because you had to use the compiler to compile the code. And this is the example I showed before, how speculations and checkpoints work together. And here's what we have. We have a computation. It's a heat propagation in a metal plate. It's scientific computation. So when this node fails, we'll move it computation there. All the other nodes will roll back their state a little bit, whereas this one is restored from the heavyweight checkpoint that we saved on this. Again, this node fails. We restart the computation here. All the surviving nodes simply roll back in memory their computation, and they go on with their process. Okay, so in the next just 10 minutes or 5 minutes, I'll talk about this ongoing work, this new project that we started, and then I will conclude my talk. I'm sure many of you have heard this question: have you fixed your bugs yet? And by the way, this is not a typo. It's actually what we call our system. And even though we might come up with new programming models that help write better programs, software bugs will still be there. There might be conceptual bugs that we have. We did not understand really what the problem was or how to implement it correctly. And while there are existing tools that may help us identify or fix certain bugs, we can use log and replay. The typical example of this is you have printouts, and then you look at the log and try to replay your program and see what went wrong really. We also have model checker, where you come up with a model and an abstract model of your program, run that, and then do an implementation and hope that the two match. But these tools don't really scale very well to large systems. And we have others. We have checkpoint and rollback. This can take care of certain types of bugs where you say there was a race condition, and if I roll back my program to a previously safe checkpoint, maybe I can pass that. The resource won't be shared between the same processes, and I'll get by. But think about the extra work that you actually have to do to get this running in a distributed environment. You cannot simply restart one of your computations while the others are still going on, right? You have to roll back all of them to a consistent state to get a consistent computation. And this is a classical, if you want, classical fixing mechanism where you identify a bug in your program, but your program is still running. Maybe you launched some application and you realize, the protocol that I have is not quite correct. Maybe I need to update this. So you have there are some academic projects that are concerned with how you can dynamically update your code. Code is running, you inject some things into it, and you make it run perfectly. But again, what does this involve in the context of the distributed system? Can you do it simply like that? Maybe not. If you just update one end of your communication, if you have two processes that communicate with each other, and you update a protocol on just one end, then the other node will be lost. So what do you do there? So few of these tools work well for distributed parallel programs. So what we're trying to do, we're trying to make the distributed component of this, easier. And why is it hard? It's hard because of several reasons. Traditional tools, they sometimes may be making use of perfect information. You have your logs there, you have your core dump maybe on your local machine. You put the debugger through to analyze that for you, and you debug your code. In a distributed environment, this might not be doable. If a node catches on fire somewhere else, what can you do about it? And the other thing is, some of these tools that I mentioned, they're really interested in restoring exactly what happened to your program, right? They want to trace the execution patterns to tell you this is what went wrong in this particular run. But would this really help you find your bugs? Not necessarily. What you really want, you're really concerned with what went wrong with your computation, what is wrong with your program, rather than the exact instance in which it failed, right? So by adapting some of these requirements, we might be able to come up, do some engineering, do some research. We believe we can come up with a better system, something that will help us, help programmers debug distributed applications. And this is how we envision all these components of our system interacting with your computation. So you have a distributed computation here, and processes exchange messages, communicate with each other in various ways. We do hope to be able to gather this global log, global log of all these actions, so that we can still use a replay mechanism for certain things. And where this really proves to be very useful is that if one of the nodes dies and there's log associated with it, it's unrecoverable, maybe we'll be able to figure out its execution based on its interaction with the other nodes in the system. So if we have a model of that node that failed, maybe we can play that along with the log messages and figure out what really happened or what could go wrong. Now, traditionally, you have your execution, and at some point, your processes fails. Ideally, you'd like to have what we call the time machine, a mechanism to roll back the entire state of the system, the nodes at least that you care about. So this is the other important thing to mention here, that if you use a mechanism like speculative execution, for example, you only roll back the nodes that you have interacted with since your last speculation or since your checkpoint, right? You don't have to really restore the state of the entire system, all the nodes in the system, all the nodes that you care about. Now, once you're here in a consistent state that maybe you can reason it's correct, certain invariants are still valid, you can feed this to an investigator. And this is what I mentioned before, a model checker. But maybe it's a model checker for actual programs rather than for abstract models. And why do we believe doing this might work rather than just using it in the first place, because you're not modeling your computation all the way from the beginning. You're just fitting it midway through and say, I'm actually very close to this crash that happened. So I know this is a consistent state. Can you explore all the possible execution, or at least to certain depth, and give me back feedback? What went wrong? Now, once you have that feedback, you don't really want to necessarily investigate all possible execution ad infinitum. You just want to say, this is what I have for running 100 levels down. I fill this to the healer. And the healer is not, it's the combination of user and dynamic updating tool or whatever other tool we can find there that would help you, once you figure out what the problem is, help you inject correct code in that state there, and lets you bypass this error and continue execution, without actually having to crash your programs. So, in conclusion, I'd like to say just a few words. I believe that reliability is really more difficult to achieve in the context of distributed systems. And just to paraphrase Leslie Lamport, the problem here is that a program you really never heard of could prevent you from doing useful work. Something that you never even knew it existed could prevent you from doing useful work. And we need to overcome some of these problems, try to come up with new programming models that would alleviate some of the problems, some of the issues related to software reliability in the context of these environments. And my solution to this is, come up with this idea of speculations, which is a transaction with no isolation. And I believe it does a good job of addressing some of these issues. It's not a perfect solution, but it's a step forward, and it could certainly be improved further. So thank you very much for your attention. I hope.
So I have a question.
Sure.
On this topic, easier. So going back to Leslie's statement about some program that I've never heard of caused me not to make progress, it seems like you've done absolutely nothing for that. What I mean by that is some program that I've never heard of that just communicated with somebody that I've communicated, they're going to abort, and that means everything that is in that causal future I now have to roll back. I guess what I'm really trying to get at is, what do you think you've made easier?
What I made easier is I made, for one, so there are three things. One, if you use speculations for certain types of applications, you can replace the error recovery code. So you don't really have to worry about if your computation aborts. Let's say you're in a distributed computation. You don't have to worry about sending messages to other nodes in the system saying, oh, the computation that I have here is wrong. So I'm hiding some of the communication details. What this makes for you, this is one of the main advantages, it makes your program simpler, right? So you just say speculate, perform these operations, abort or commit based on the assumption that you have. When you have simpler programs, you can reason easier about their correctness. You don't have, assuming that the rest of the components are doing the right thing and you know what their specifications are, then you can say, I know these components are correct. I'm going to make use of them, and this is what my code does. Is it correct? Does it perform to the specifications that I want? So this is one of the main advantages. The other is that you have, in the context of distributed systems, you can reduce or you can optimize the computation by having distributed optimistic execution, where the fact that certain nodes pass asynchronization points optimistically doesn't have to mean that they have to write ugly code to restore their state, or that they have invalidated an invariant in the system.
I think you talked about kind of eliminating the wait for the last message.
Yes. Yes, you can say that, maybe I haven't done much on this remote system preventing you from doing work. But if all programs were actually written with higher level abstractions, then maybe we could be able to reason about their characters better, and maybe this would alleviate some of the the software problem of software reliability. So it might make other people that write this remote software write better software, which could fix the issue.
Thank you.